Hi, I'm Norman Wildberger, and today I'm going to give you some highlights from triangle geometry, a subject that goes back thousands of years, but really was developed mostly in the 18th and 19th century. A lot of the development of the triangle geometry actually owes to high school teachers, especially in the latter half of the 19th century. They made an important contribution in delving into deep aspects of triangles. So here's how we'll start with the triangle A1, A2, A3. That's our basic triangle. And I remind you of a few special points related to that triangle. First of all, the point C, the circumcenter, the center of the circle which goes through the three vertices of the triangle. The centroid, G, which is the intersection of the medians. A median is a line from a point of the triangle to the midpoint of the opposite side. That's the centroid. And the orthocenter, O, is the intersection of the three altitudes of the triangle. So we drop a line from A3, say, to the other side, perpendicularly. That's called an altitude. So there's one altitude, there's another altitude, and there's the third altitude, and these three altitudes intersect at the point O. Now it was left to Euler, the greatest and most important mathematician of modern times, a Swiss mathematician who spent a lot of his life in St. Petersburg in Russia. And he made important contributions to all branches of mathematics, but in particular he discovered that these 3 points, C, G, and O, always lie on a straight line, no matter what the triangle you have that you start with. So this line is now called the Euler line, in honor of Euler. And he also noticed that there was a certain ratio between these 3 points. OG was always twice GC, always in the ratio of 2 to 1. OG to GC equals 2 to 1. A little while later, Feuerbach and others investigated another circle, the circle that goes through the 3 midpoints of the triangle. That's called the 9-point circle of A1, A2, A3 because it goes through not only the 3 midpoints, but in fact 6 other points. It goes through the 3 feet of the altitudes. So there was an altitude, and by the foot of the altitude we mean the point where that altitude intersects the opposite side, perhaps extended. So there's 1 foot of the altitude, there's another altitude, there's the other foot. The third altitude has that as its foot. So they are the 3 feet of the altitudes. And furthermore, there are also 3 additional points formed by taking the midpoints between the orthocenter and the corresponding vertex along the altitude. So if we take that segment and take the midpoint, we get that one. If we take this segment, the midpoint is that one, and this segment, the midpoint is that one. So these 9 points all lie on a circle, which I'm going to draw for you now. So that circle is called the 9-point circle, and it goes through these 9 points for any triangle. Alright, let's say a few words about vertex bisectors. A vertex, by definition, is a pair of lines, a pair of intersecting lines, like that. Right. So if this is the line L1, and this is the line L2, then this configuration, the set of L1, L2, is called a vertex. Now, a vertex like that has a bisector. In fact, it has 2 bisectors. What is a bisector? It's another line, in this case one of the blue ones, that makes equal spreads with both of the given lines. Okay? So that is one vertex bisector, and that's another vertex bisector, and they are necessarily perpendicular. So here now is a reference triangle in black. So triangle there. Now, these vertex bisectors meet in 4 points. These points are called incenters and excenters. So there's a point of intersection, there's 3 other points of intersection. In many treatments of geometry, these incenters and excenters are treated differently. The incenter is treated somehow specially, but it's probably really important to think of these 4 different ones as all aspects of the same thing. Now what I've shown you here is that each incenter actually has a special property. And that is, say this in center here, that is the center of a circle which touches the three sides of the triangle. So if you look here, then in red, it's the center of a circle, and that circle touches the three sides of the triangle. This in-center, or X-center, also has that property. The three sides of the triangle are these, and there's another circle centered there that's tangent to the three sides. That X-center, there's another circle. That X-center, another circle. Now, a beautiful property of the 9-point circle of the original triangle, discovered by a mathematician called Feuerbach, was that that 9-point circle, here shown in green, is tangent to each of these 4 in-circles or X-circles. Tangent means that it just touches each one of these circles tangentially. Just fits in there beautifully, no matter what triangle we started with. All right, in the 19th century, in the last half of the 19th century, people discovered a remarkable involution on points with regard to a triangle called isogonal conjugation. It's a big word. I want to explain what that means. It has to do with reflection in a line or in a pair of lines. So let's have a look at this line here and its perpendicular line. Let's just start with that one. There's a notion of reflection in a line. So let's say that point there or that point there. These are reflections of each other in this line. And what does it mean? Well, it means, say, to go from here, we draw a perpendicular line to the given one, and then go an equal distance or an equal quadrants to the other side, to go from that point to that point. So that's called reflection in this line. You can not just reflect points, you can also reflect lines. So this point here, under the same reflection, goes to here, and in fact every point on this line gets reflected to a point on this line. So we can say that in this line, the reflection sends that one to that one. It sends a line to a line. And it's interesting to observe that that definition is also exactly the same as reflection in the perpendicular line. So if we reflected this point in that perpendicular line, this point would go to that one would go to that, and that line would also go to that line. So reflection in this line, when we talk about lines, is the same as reflection in its perpendicular line. Let me explain to you this beautiful idea of isogonal conjugation. All right, now suppose we have a point P, which is arbitrary. We connect P to the 3 points of the triangle with 3 lines. And then what we do is we reflect each one of these lines connecting P to a point of the triangle. We reflect that line in the vertex bisectors at that vertex. So these are perpendicular, so it doesn't actually matter which one we use. Let's use this one. If we reflect this line in this vertex bisector, we get this line right here. Okay. If we reflect this line in this vertex bisector, we get that line there. That goes to that. And if we reflect this line in this vertex bisector, we get that one. And lo and behold, the 3 reflected lines intersect at a new point. That's called going from P to P star. That's called isogonal conjugation. It's a remarkable fact. There's a few more examples. You can check that that point there has isogonal conjugate that one. And if you do it twice, you get back to where you started. Very interesting property is that the circumcenter of the triangle and the orthocenter are isogonal conjugates of each other. Next time, we'll talk about more highlights from triangle geometry. I hope you'll join me for that. I'm Norman Wahlberg. Thanks for listening.